Hello everybody and welcome to CS302 Online. I just hit the stream button. I didn't realize I was not streaming while the countdown was happening. So uh, hopefully you guys are all alive. So alright, today let me go ahead and scroll this up. I was writing some stuff to save some time. Today we are going to begin a new phase of the content of this class because we are going to start talking about trees. However, I would like to wrap up our discussion in sorting by briefly going over the differences between Quicksort and Mergesort, which are the best of the sorting algorithms that we have covered so far. All right, so for that I have a little chart that I got from Geeks for Geeks that I post on Canvas that shows you kind of like the comparison between them. And what I'd like to do now is kind of spend some time looking at this chart to kind of discuss the differences. So I'm going to go ahead now and hopefully you'll be able to read that. So there we go. And this is the source where that is from. Okay. So we got a couple of different categories here, and I'd like to start by talking about the bottom one, actually, locality of reference. And so this is a concept that if you have not taken 219 will be sort of foreign to you, and that's okay. It's not something really that we talk about in this class, but I would like to sort of introduce that. And so if you'd like to know more, you can always watch my 219 lectures that I did over the summer. I have the full class there. But ultimately what the principle of locality is, which is where this is coming from, is the idea, there's two of them. There's spatial locality and there's spatial locality, I believe. Spatial means time and spatial means space. Maybe I'm mixing those. But anyways, there's locality in terms of time and space. And what it means is that when you're working with some data, it is very likely that if you work with a specific part of data, of like an array, more than likely you're going to come back and work with that same data again in the near future. Similarly, that's time-based. With space, it has to do with the fact that if you're working with a piece of data of, for example, something in an array, there's a high chance that the next thing you're going to work with is whatever follows in the array. Let me give you an example of something that would follow that principle. Suppose that you are printing out an array, and the array is of size 10, and you're working on the fifth element of the array. The computer, if it's trying to predict what you're going to do next, if you just access the fifth element of the array, it says there's a very high chance that this person is going to access either the sixth element or the fourth element. It doesn't know if you're going forwards or backwards, but it's like there's a very high chance. And it happens that it makes this guess based on the fact that very often when people are working with data, they're working with the data and the neighbors of that. An example of like being with the array. So if you're printing an array and you just printed the fifth element, you're very likely going to keep printing that array in the same order, or you might be printing in an order backwards. It doesn't know, so that's why it looks at the one before and after, right? And when it comes to, again with time, if you think about a program, your program is involved with variables, some loops, some function calls, some other loops, some function calls, and so on until you get to the end of the program, right? But the biggest things are going to be your loops, function calls, and I suppose if statements mix and match around there. And so because of the loops, more than likely you're working with a subset of the data on those loops, and then you move on to some other data, right? And so when you graph the usage of certain variables in memory, you will see that it usually follows some sort of curve like that. And so what happens is, let's say this is for an array called A, and then this is an array called B, okay? And so what happens is you see that you use this array A a lot to the point that it's used very high frequency here, and then it sort of wanes off and you don't use it again. And then maybe use a different array called B. And these could of course overlap, but what I'm saying is that typically usages of certain pieces of data in your program kind of go up and then come down. When would you be using the array the most here? That would be like when you're like sorting the array, for example, or sorting this specific piece of data, and you're really like in a for loop or something, okay? Whereas down here, maybe you're just referencing like a specific index or something, right? And so this is what you typically see happen with both time and space. And so that's what locality of reference is. But like I said, if you want to find out the full details and everything, I have a lecture on that as well. I mean, I don't know why I can't remember the name. So spatial is time, spatial locality, temporal locality. That's the other one. Yes. Okay. So spatial is space. So that's spelled like that. And then you got temporal, which is for time. And they're both so the spatial locality and temporal locality, and they both form the idea of the locality of reference. And it's a very, very important concept that you should know when you're trying to optimize a program that's running. Because I was just talking about this a little bit in the 202 lecture. If you, the other things you learn in 219 is that space is very expensive. And so, if you have a big program that doesn't fit in main memory, then which parts should you load ahead of time to predict the usage, right? And so you use this locality of reference concept to try to load things that may be used in your program next, right? And so, even further than that, there's things known as cache, which you'll learn in 219, which are even faster segments of memory than RAM, and they're closer to the actual CPU. But those are on the megabyte size. So you have to be very, very, very careful of what you want to put in there ahead of time and what you can keep in there to speed up your program even more by factors of 100. Okay? So this is what is in your future for 219. But for now, what they're talking about here with the locality of reference in terms of the sorting algorithms is that an algorithm like Quicksort has a high locality of reference, whereas Mergesort, they're saying it has a poor locality of reference. What that is saying is that when you're loading and you're working with a partition on on Quicksort, is you start out by you have two indices, the I and the J, and they start, or the high and the low, and they start at both ends and they work their way in, right? So the fact that you're working with the next element one after the other, that is a good spatial locality. And furthermore, you're only working with that specific subset of the array, which I guess that also applies for Mergesort in a way. So it's good in that sense. Okay. On the other hand, with Mergesort, when you're merging the list, yes, you have two indices and you're sort of merging together. But the thing is, you may have finished merging something, but then you're working with something completely different, so it kind of lowers that locality. So it's something that actually, the algorithm itself, you can say it's n log n or n squared, but we're still considering that access time for any element given a specific index is immediate, right? So if I, and we consider that with arrays, right? We say, oh, I can immediately access the 5th element of an array or the 10th element of an array and so on, because we assume that that's the case. But we know in practice it's not really the case, because you can't load a big array, and by big, I'm not even saying like millions. I'm saying like, well, maybe high thousands of depends on what you're storing, I guess, because numbers you can load a lot. What I'm saying is, you can't load sometimes an entire array into like a cache when the cache is like 8 megabytes. And that cache is not just for your program, it's for the entire computer. And so that is going to actually affect performance to the point that you may actually want to, you might say, well, Quicksort is at n squared and Mergesort is n log n. But yeah, Quicksort's locality of reference being higher will actually help the algorithm finish faster. And so Timsort, which is the one that a lot of the implementations use, like if you call the sort function, which is a combination of Mergesort and I believe Insertion sort or Selection sort. I always get them mixed. I think it's Insertion sort, but that technically doesn't have as high locality of reference as a Quicksort, but it still turns out that it's better. But that might be something to consider as well. So yeah, on the terms of stability, Mergesort is a very, very stable algorithm, which is great. Quicksort is not, as you can see, because of the when you're swapping things around with high and low, it might unorder duplicate keys, and so that's kind of a given. If you have something that is almost sorted, Quicksort may actually mess it up before it sorts it, and so in that case, Mergesort might be more beneficial to use, or actually, technically speaking, if the list is almost completely sorted, like almost, in that case, insertion sort might be better, right? Because that's I gotta make sure I don't get the mix. Insertion sort is the one where you're inserting as you go. So like you look at the list until you find something that's out of place, then you go ahead and you insert it in the right spot. Selection sort is the one that's always n squared. So it's insertion and merge sort. Okay, that's what I thought, because selection is always n squared. So yeah, thank you for clarifying that. So Tim sort is insertion and merge sort. That's what your colleague was saying. So, and then of course you see here where it says prefer to erase and link list, which is why that's how I set it up for the assignment. Because the beauty of linked list is that you can very easily split and combine things together. And so while the auxiliary space, which we typically refer as the extra space aside from the list of data itself, with merge sort, when you're combining it, you need a brand new array, right? Well, the cool thing about the linked list implementation of merge sort is that you don't really need it, because you have all your nodes and you're just basically playing and swapping them around as you want, but you don't need extra space. So that, I suppose, is one plus for the linked list version of merge sort. Even though here it says additional storage space requirement, but you don't really need that if you're working with the linked list version of it. If they're both arrays, then yes, merge sort will need additional space. So that, is a little bit of an argument there. Okay. Don't take this one too seriously. Ignore that one. Which other one would be good? I mean, I guess the asymptotic complexity is n squared versus n log n, but again, that is strictly dependent upon your pivot. The ideal pivot being the median value, but finding the median value itself takes time, which defeats the purpose. So again, one of the best ways is just to pick a number at random and hope for the best. And usually works okay, but we saw a case where it didn't when I first showed you Quicksort. So ultimately though, the theta of both of these is going to be n log n. So, but as you saw, merge sort and insertion sort is better. Now, something big to talk about is parallelizing an algorithm, which of course, theoretically, the lower bound of comparison-based sorting is n log n, which means we can't really do better than something like merge sort. However, you can parallelize things. And they'll talk about Amdahl's law in 219 and the certain limitations about parallelizing, because like if you have a task that takes 10 seconds to run and you split it between two computers, it's not going to be exactly split into two, because there's coordination time to get both computers up and running, run the task, and then merge the results together again. So a program is typically split into two parts: the part that you can parallelize, and then the parts that have to be sequential or cannot be parallelized, which is typically the beginning and the end of the program, if it's something that is easily parallelizable, which we call embarrassingly parallelizable, which is what merge sort is. Because merge sort is great for, once you split the list into two parts, those two parts can run at the same time, and the only time that they have to kind of work together is at the end where you're merging the big chunks together. But in the meantime, you can split them into as many nodes as splits as you have. The downside, of course, is going to be the communication between the different nodes in the computer to basically sort. So you have to have the comparison pro and con of like, how long does it take for me to send this data to a different node? And by node, I'm talking about a different computer in like a supercomputer network or something. So how long does it take for me to communicate this information to a different processor with its own set of memory and whatnot to be able to work on this sub-problem? And if that time is less than the time that I'm saving, then that's okay. But if the time is more to communicate the time I'm saving by sending it and splitting the workload, then it's not okay. And so there's a certain limitation on how much you can parallelize something. But I will say, as a quick sort of number, I'd say 90% you can speed up, basically. So like you could if you have something that takes 10 seconds to run, you could potentially run it in like 1.1 seconds. If of the 9 seconds you can split and make them all basically run together, you could achieve something that fast, you know. But that 1 second you're never going to get rid of, because that's the time it needs to basically split and rejoin. So anyways, Mergesort, and I think that's probably the reason why primarily that TimSort and in general the sorting algorithms that you see in your like Python and whatnot that are built in are using the Mergesort, because it allows you to parallelize better. And nowadays most computers have multiple cores, multiple threads, and they're able to run things in parallel and take advantage of that versus sequential. Okay, you can't. You know, if you have 8 digits that you're sorting, 8 numbers that you're sorting, you can't cut ahead of time until you finish a partition, right? So like if you have the first partition, you got to partition in Quicksort, you got to partition that into the left and the right, and then you can send those to different computers. But those two need to finish their own partitioning before you can split it against 4 computers, right? So it's not as, it is possible to parallelize, because once you've split that partition, that initial partition, once you split it into 2, so like, you know, if you got yourself Quicksort with something like this, you know, and then you got your pivot, and then you got your 2 partitions, eventually you end up with the pivot bin here, hopefully something that is somewhat balanced, but no guarantees again, that's why it's O(n) squared, and you got your left and right partitions, right? Then once you finish that first partitioning, which does take time, potentially can take n time to do, well, not potentially, it has to take n time because it has to look at all the numbers. So it's going to take n time, right? And then now you split it, and then you can have the left be done by one computer and the right be done by another computer. What it will typically be is like, if this is computer 1 that does the splitting, then computer 1 can finish doing the left side, and then computer 2 is going to do the right side. And at some point, you know, when it comes time to finish, there's no merging required, because what's going to happen is this is already like sorted, and then this is sorted eventually. The only sort of merging is more of appending. You just kind of have to like put this at the end of the list. You know, if you're storing it back into 1, you can send this, but you can do this sending back at any time. So and also there's no guarantee that these will finish at the same time, because it depends on how nicely the thing splits evenly. Whereas Mergesort is more consistent in that matter. Okay. So yeah, I think that's all I'll say about that. If you want to know more about parallelizing, they'll talk about that in 370. I think that's all I wanted to point out. Just go ahead and look at this. Might show up on the tests, I don't know. I did finish the test though. So yeah, okay. So I think that's all I want to say about Quicksort versus Mergesort, unless there's any specific questions on sorting in general. I don't know if you guys have anything that you want to talk about. Otherwise, we shall move on to trees. So this is where the class gets far more interesting. So far, you know, sorting, stacks and queues, linked lists, like whatever. Trees is where things start to get cool. And then from trees, we sort of expand into graphs, which is even cooler. But along the way, we talk a little bit about hashing and whatnot, which is nice too. But trees is the cool part. And that's where the assignments start to get very interesting. Now, of course, trees are pointer haven. So like, yeah, that'll be kind of interesting. So in fact, I will be releasing the next 3 assignments probably after the test, so you can get going on them. So yeah, good times are ahead. So for the trees, what I like to do is there's 3 links in Geeks for Geeks that have an introduction of trees and some properties and some examples of special cases of trees that have a special name associated to them. And that's what I kind of like to sort of base the introduction of trees on before we sort of start talking about traversals. So if you want to follow along, you know, I'm going to go ahead and post the link here, and I'll post it also on the YouTube description. But yeah, just you can follow along like that. That's the first one, and then we got the properties one, which is what I was writing ahead of time in class. And then we got the special kinds of binary trees, which are useful to know. because they have special situations that make our life easier. So the first thing I want to say about trees is that they are unlike anything you've seen before in terms of like arrays, stacks and queues, and even linked lists, which would be, I suppose, the closest thing that you've seen to a tree. Because technically speaking, a linked list is a type of tree. It's what we would consider a unary tree. But what we're really going to be focusing this class on talking about, at least before we get to graphs, is binary trees. That's really what this, the title should be of this lecture today. And so trees, as the notes say, are hierarchical data structures, okay? And so this is a very different sort of concept to really understand than what we've done so far. Because we consider something to be ordered, like an array to be ordered or a linked list to be ordered, we are considering, again, with sorting, right? Like something is in ascending order, non-descending order, non-ascending order, descending order, all these different terms. That's what we consider to be sort of an organization of that kind of data. However, nothing prevents you from doing a different kind of organization within a array and whatnot. In fact, I'm going to show you when we get to like heaps how to store a tree in an array. So it doesn't have to all be about pointers technically. So the difference being, if you're storing a tree in an array, is the order that you're storing things. That if I show you right now, if I showed you an array containing a heap data structure, you would be like, this is literally random data. Like I could have literally put on your test like sort this using Quicksort, and it's actually a heap, and you would never know. And it doesn't matter because it looks just like garbled up data. And what matters is how that data is actually organized depending on your algorithm, which makes it no longer just random data, but actually significant. And with trees, that significance is a hierarchy. Trees are all about hierarchies. Now, what's a hierarchy? Well, the best example of a hierarchy that we're all aware of is how computer organization works. So if you go ahead and you look at your directory, whether you're on a Macintosh or you are in a Windows machine or a Linux machine, you typically have some type of home directory or C directory, or what's it in Mac called? It is I think it's also called home directory, or it has your username directory and whatnot. But either way, suppose you make a folder somewhere in your computer, right? And we're going to call that folder 302. In fact, this is what I personally have for handling the class. Inside of this folder, I decide that I want to store all material related to the 302 class that I am taking as a student. Okay? So I'm a very organized person, so I'm going to take a couple of different directories. I'm going to go ahead and make a directory for the syllabus on its own. I'm also going to make a directory for my homework assignments. And then maybe another directory for the worksheets, because maybe these are the programming assignments. And then maybe another directory for, what do I have? Well, the exams I have, but you wouldn't really have one for that. But maybe study guide in your case, right? And hopefully there's no directory that has like a little pirate on it, because technically the book for this class is free. So hopefully you're not like pirating a free book. But yeah, but you might actually have, in this case, because it's a free book, you might actually have the book PDF that is freely available because the book is free, right? Or you might actually have downloaded some pages from Geeks for Geeks and have as reference. Kind of how I have a printed version of that right here. So don't be scared, dog. Don't be scared. My dog is here. So anyways, it is free. So like, yeah, you got scammed if you paid money for it, or if you have to like go to like shady places to download it, then that's a big meme. So yeah. All right. So anyways, from here, you might go extra organized, because I don't know about you, but like, at least even so far right now, you have multiple C++ files that you've been working with, and there will be a lot more. So you probably have this separated. This is how I have it when I first created the assignments. You know, I have these separated by numbers. I think I call them like assignment 1. This might be a security risk of me telling you the structure of my directory, but you don't know where it's hosted. So yeah. So, and if you find it, then hey, kudos to you. But yeah, so essentially I have different folders for different assignments. I'm within there, then I actually have the contents of the assignment. So I have like a C++ file, you know, maybe the PDF, then a LaTeX document or Word document, depending on what I'm doing. But these are individual files, so we don't really care about that, okay? Under the worksheets, you might also have them separated by numbers too. I have them like that actually with LaTeX source file. Oh wait, actually no, those I do in Microsoft Word. So yeah, and then with the assignments, I also have like 1, 2, and final. Okay, the syllabus, I actually, now we have a common syllabus, but like when I was doing it in person, I had different syllabus for each section because I wanted to have the time of the class on there. So I have different folders by that. But the book, I only have one thing. So that's kind of it. So yes, I'll give you extra credit, but not if you hack into my house because I don't want to get DDoS or something. But if you hack into like school server or something, into my thing, don't hack into other people's. Otherwise, I'm promoting hacking and that's going to get me in trouble. So yeah, okay. So, and I'm teaching an ethics class. This is bad to say all this stuff. So yeah, okay. So this is sort of a good representation of how you have your files stored for this class, or at least how I have them stored for this class, right? So here's the thing. And this is not even the end of it, because guess what? This is all in the folder called school. And I have other ones for like 301, 202, and so on. And this school folder is part of the operating system, you know, that I have other directories all the way up, in my case, to C drive, because it might be in Windows, right? And so, or I guess if I'm storing this in the cloud, then whatever the cloud's home directory is. So anyways, I do back up my files in the cloud just in case my computer dies in the middle of the semester. That'd be pretty sad. But yeah, so this, you know, let me get rid of this because it might look a little bit confusing. But looking back at just the 302 part, this is essentially a tree. This is a tree hierarchical data structure. You got sort of like the parent, and then you got all the children, and then you got all the grandchildren folder, and so on, right? And typically you like to draw it from top to bottom, but I could have just easily drawn it from bottom up, right? Some people might visually, you know, like it that way better, right? But most people seem to kind of like the top to bottom view, because I guess how we read is we look from top to bottom, you know, in the Western society, I suppose. So yeah, in fact, I was very tempted to do like not just that, but like to name this 1, 2, 3 in order. But like I had to like intentionally put it out of order just to make a point that it doesn't have to be in order, right? Because the folder itself can be in any order that I want. That's not what I'm caring about. What I'm caring about is the hierarchy, that these are subfolders of these. It doesn't matter the order these are in, but these, you know, that they all belong to this, and this one belongs to this. So let's go ahead and do a couple of vocabulary words that can be useful to identify a tree. Now, is this a binary tree, first of all? This is not a binary tree, because what does the word bi in binary mean? Bi in binary comes from the number 2. So binary tree is a tree with 2, and then I have to define what children is and parents. So let's go ahead and start with that. So first of all, let me go ahead and list a couple of definitions here. So we got tree, we have root, we have node, we have leaves, parent, I suppose, is a good one too, and then child. Okay? Yeah. So let's talk about what each of these mean. So the tree is the entire thing. That one's kind of what we're working with here. But these trees, they all have a starting point. Like this is going to be the most parent-most thing on the tree. Okay, so like if it's a family tree, the oldest person there, the one that's lived, you know, that was born the earliest, or in the case of computer, the most home directory. In the case of root, in the case of Linux, the root directory, which would be the home directory. In the case of Windows, probably the C drive, the actual drive name could be D or whatever. In the case of Macs, that's the one I don't usually use a lot. So I don't know what the home directory on the Mac is. I think it would just be the user directory, but I bet you that's not really it. It's probably a real, because it's probably just another home directory, because Unix is kind of shared amongst Mac and Linux, like it's kind of the same thing. So yeah, it's probably just a home directory as well, but they hide it. So yeah, that's going to be the most top part of the tree. Okay, so that is going to be the 302 in this case. All right. But most importantly, what do we call these individual squares or folders in the case of this example? And those are going to be the nodes, okay? So that's the important one, nodes. So whenever I say this is a node, I am talking about one of these. And this, by the way, comes from the linked list, right? So if you think about linked lists, you know, you got a little squares and they're all linked together, and we call each of those squares nodes, okay? And so essentially, a tree is made up of a bunch of nodes, and those nodes are connected in a special manner, okay? Ow, that kicked me. So there's two kinds of nodes that are special, and that's the root node, which is this one over here. The root node is typically going to be that topmost node, okay? The top of the hierarchy, okay? This is like a mafia thing. This would be like a mafia boss or whatever, all right? And then we also have what are known as the leaf nodes. The leaf nodes are the ones at the bottom of the tree, so the lowest level possible. In the case of the directories, it's actually the innermost directory, okay? So like in this case, assignments 1, 2, and 3, those are the innermost possible directories. Means that inside of that assignment 1 directory is just a bunch of files, but no other folders, okay? This would make it a leaf node, okay? Now, in terms of definitions, a leaf node is known as a node that has no children. So what is children? A child node is a node that is coming off of another node, essentially, okay? So we got the concept of a parent and a child. The concept of a parent and a child is that a parent node is a node that has children, and a children node is a node that has a parent. Okay, now I know that's kind of like a circular definition, so let me point it out here. In this example, we have, for example, the node that says worksheet. Okay, this node is parent to two folders or two nodes that are its children, and those are the 1 and the 2. Okay, so we would say that the worksheet is a parent of 1 and 2. Okay. On the other hand, we could also say that 1 is a child of the worksheet node. Okay, let me say node 1. Node 1 is a child of the worksheet node, okay? So it's that hierarchy that we're saying that this came from this, or this belongs to this, okay? Now, you typically don't draw arrows when it comes to trees, but if you're thinking about this from like a graph theory perspective, then you would want to draw arrows like this, okay? Kind of how a linked list, you draw the arrows going from the head to the tail. Even though we talked about how when you implement the queue, you kind of implement it backwards for the arrows because the arrows are actually pointing to the back of the line. Here, it's a little bit more intuitive that the parent is always pointing to the children, okay? Actually, I'm trying to think when you implement it, you would say like child parent is equals, yeah, do like that. All right, so we have, is root node the only node that's a parent and not a child? Okay, so no, there's a lot of parents here. Okay, so for parents, think of this like a family tree, okay? You know the saying that's out there in the world that say like, this person is child to someone, but could also be parent to someone. So you are both a child and a parent. The same thing kind of applies here. I don't know how that saying goes. I probably messed it up. Let's look at, for example, exam. Exam is a parent. You know, it's a parent. It's got 3 kids. It's got 1, 2, and F. But also, it's a child itself, 2302, right? So like your dad or your mom. I hope they're in health. But your dad and your mom, they are your parents, right? But also, they're somebody's child. In fact, 2 people's child, right? Unless you're like Anakin Skywalker, who, you know, the Force made her only from her mom, right? So, or I guess like, no, I was gonna say like the religious person, but that was like, ooh, that's a minefield. So yeah, but anyways, Anakin Skywalker, right? That's a good one. Anakin Skywalker only had 1 parent, which was her mom, and then the dad, there was no dad. So the mom just got pregnant. So that's kind of the same thing here. So Anakin Skywalker has a parent. And then Anakin Skywalker is a parent himself to Luke and Leia. Spoiler alert. Okay? It has, oh, I see what you're saying. So yes, the only node that is a parent but not a child, you are indeed correct, would be the root. The root is like the first being. It just appeared. There's no parents. It just like came from nothing, okay? So yes, you are correct in that sense. 302 in this case is a parent and not a child itself, okay? But if this was part of some sort of bigger hierarchy, then that would be invalidated, okay? So in our case, the C drive, the D drive, those are probably the root nodes, and they have no, they're not somebody's child, okay? So yeah, I got you now. Sorry I didn't get your question in the first place. Okay, so all right, so we understand the concept of parent and child, the concept of a root node, and then the concept of a leaf node. So the leaf node is going to be the bottom layer. Leaf nodes are children, but they're not parent themselves technically, right? So like, I don't have any kids, so I am a child of someone. I'm a child of my parents, but I'm not a parent myself, right? So I'm a leaf node until I decide to have kids, and then I would also become a parent node, okay? So that's the other extreme. On one side, you have the root node, which is nobody's child, and then the leaf node, which is nobody's parent because they don't have kids, okay? And then the entire thing is known as a tree. Now, how do you decide what kind of tree it is? So that binary part. All right, actually, don't want to use that color because you get confused. So this is brown. Okay, so the number of children that a node has is sort of like the degree of it. Okay, and so the tree, the name of the tree, whether it's a unary tree, binary tree, ternary tree, 1000 nary tree, so like, you know, different names will be unary, binary. I was gonna write trinary, but it's ternary. And then 4, I don't know, but I can just say fournary. And then like over 9,000 nary. Okay, so what this is saying is that how you decide what you want to call a tree is going to be based on the parent that has the most amount of childs. So like if you're looking at your family tree, you're going to look for the sibling in your tree that had the most kids, and then that's going to be the name. So if your family, like as long as you go up in the family tree, the person that had the most kids was like Uncle John, who had like 4 kids, then this would be a fournary tree. If no one in your family had more than 2 kids, then it would be a binary tree. But if you had some guy who had like 20 kids, then it would be like a 20-nary tree. Okay, like I have an uncle who, the story goes, he had like 40 kids with like so many different ladies. And so like, I suppose my family tree would be like a 40-nary tree or something. So yeah, not an uncle, but a grandparent uncle. My mom's uncle, I think. Yeah. So I just called out. So yeah. Okay. So yeah. So essentially, that in this case, if we look very carefully, technically this doesn't have any nodes, and this one didn't have any nodes that I saw. But I mean, well, actually no, I did say I have different syllabuses, right? But this semester I don't, so I guess I won't put any. Okay. So in this case, because of homework having 3 things in it, then this will be a ternary tree. Okay. That would make it a ternary tree, because this one does. I guess this one does have folders for each one. So this one we'll say there is folders 1, 2, and 3. Well, F because of final, right? So this will be a ternary tree. However, if I drew a binary tree, that would mean that it would be something of this format. So a binary tree can have up to 2 children, but no more. Otherwise, it's simply a naming convention. But if I'm saying you're making a binary tree, you cannot have more than 2 children at any given moment. Okay? It's like if you know how China had the one kid law or one child law for a while. That would be like a unary tree essentially. Their family trees would be like unary trees basically. All right? But then they removed the law, so now you can have any n-nary trees basically. I suppose the generic term would be n-nary. For like whatever. All right, so in this case though, a binary tree doesn't have to always have 2 kids. Like for example, if we look at this example here, we have here, yes, this is binary, this is also binary, and this is also binary. However, this one's technically unary. This one only had 1 kid. Okay, so yeah, and also you have the situation of 0 kids, which are of course the leaf nodes. So like nothing here, nothing here, nothing here, and nothing here. All right, so Darwinian, that you guys are getting too biology for me here. Okay, but anyways, so yeah, the top. I guess a good way to how they state the root node. The topmost node is called the root of the tree. So yeah, that's a pretty good one there too. Okay. Let's see what else I want to point out from this. Oh yeah, I guess why use trees? Like why make your life hard? Other than, of course, trying to represent like a computer drive. Would a doubly linked list be considered a unary tree? That's kind of a iffy one. So technically speaking, like there's an argument to be made that yes, you could consider it a binary tree, not a unary tree, binary. But also, you could argue that it's unary. Like the fact that you can go back and forth is kind of like it can be made an argument both ways. Frankly, I would just say unary because it's just a linked list. But know that if somebody made an argument that it could be binary, they could be technically correct, because what is happening is you still have two children. Like there's 2 pointers in a doubly linked list. It just happens to be that you know, if this is coming like this, that this is kind of pointing this way, so it's like circular, so it's kind of weird. That's the other thing about trees that I want to point out. This is not a requirement of trees, but like when you're talking about binary trees, you don't ever have a circular reference. Like there's no inbreeding going on, essentially. Okay, so like you don't have like the child node linked to the grandchild node going in circles like that. Okay, that would be bad, and so we don't have that here, essentially. Okay. So, but yes, you are correct. Some data does beg to be ordered hierarchically, and there's some examples on that. I remember there's some examples in here. I don't see them now, but I'm pretty sure they had some other than like computer directories. But more importantly is why we want to use it. A tree can contain a circuit. It's not called a circuit. It's called a cycle. We'll talk about cycles when we get to graphs. Maybe, yeah, because I don't know, circuits is kind of like an EE term. But yes, cycle will be the official term. If trees contain cycles, because technically speaking, see, we're jumping like a month ahead of time. But technically speaking, a tree is a directed acyclic graph. That's kind of what a tree is. It's a subset of that. It's directed, which means there's arrows, which means they only go in one direction. It's acyclic, which means there's no cycles, or as you call them, circuits, and it's technically a graph. So yes, trees are that. I was not gonna bring up that until a month from now, but I guess it appears. That's why I'm deleting it, like we're hiding it. But yes, that is the end game. That's why the discussion naturally evolves from trees into graphs, because this is literally it's like a small picture of the big picture of graph theory. So yeah. Okay, so this is important. I want to point it out. So one of the big advantages of trees over other data structures, there's pros and cons like anything, but let's talk about the pros first, because nobody wants to hear the cons first. And that is that it provides a lot faster access time or search time. Okay, so with a binary tree, for example, and there's of course special scenarios here to achieve this, but if I have information in a tree like this, and I do specific things to this tree, which are called a binary search tree, that I say that any number here on the left child has to be smaller than the parent. So like I can have anything less than 5 on the left side. And on the right side, I have to have anything bigger than 5. So maybe like an 8. And similarly, the same applies here. So I have a 10 maybe here I have a 1, and here I have a 4, okay? So by ordering my data in this sort of hierarchy, I can very easily search the data in a much faster time than if I was to search something linearly. In fact, this kind of reaches into the situation of binary search, if you think about it. Because now, all I need to do is two comparisons, and bam, I've identified whether a 4 exists or not. Because if a 4 did not exist, let's say I'm looking for a 7. If I'm looking for a 7, I first go here, but then I hit this 8, and I see that there's nothing over here. Because there's nothing there, it means that there's no 7 here. We'll talk more about this special scenario of binary search trees, but what I'm trying to get to is that it does improve the big problem that linked lists have, which is access time, right? If you want to search for something in the linked list, you can't use binary search. You have to use linear search, even if it's sorted. We are solving that problem with trees. That's the big benefit right there, is solving that issue. Technically speaking, this says here that trees are slower than arrays. there's an argument to be made about that because trees themselves are not something that you have to implement with a linked list. It can be implemented with an array. So it's arguable. It is arguable whether or not that is true. I don't want you to associate trees with linked lists or with pointers. Trees is a concept that can be implemented in different ways. Most typically, yes, it's implemented like a linked list with pointers. But like I said, there's heaps which are typically implemented as an array. Like there's no reason to implement a heap as a linked list. While you can, it's not beneficial. Would the for require rebalancing? No. We will talk about balance trees when it comes to AVL trees. But as this is now, this is technically considered a balance tree under that category. But that's getting a little bit ahead about that. But yes, I'm glad that you guys kind of know these terminologies though. This is good. Sometimes I go into this class and people are like they have no previous knowledge, which is okay. But you know, it does strain confidence that you guys know this stuff. Talk about insertion. So in here it says tree provides moderate insertion and deletion. So here's the thing. If you're storing this as a linked list sort of system with pointers, then you have all the benefits of a linked list, which is like you don't run out of space, and then you can pretty much append things wherever you feel like it. Now, if you're following the rule of like something being only binary, but that'd be like a binary tree, then there are special, like you can't just append something to the tree because that would violate that rule and make it a ternary tree, which is okay if that's what you want to do, but if you want to keep it binary, then that's not okay. And so in that situation, you know, if you wanted to put a 2, it would actually have to go here. We'll talk about as to the reason as to why it would go there, and as your colleague said, how balancing gets involved in this, because you get these benefits of faster access time, faster deletion time, but there's a cost to this, and that is to maintain the height to be good, which it would be a log n height, which again is something that we'll talk about more in detail later. This is more of like an introduction to the trees. Okay, so here they say quicker than arrays for insertion, and then slower than unordered linked list. I agree with the unordered linked list part because that one is just like of one time you just append it to the beginning or the end. So fair enough, I agree with that much. So and I guess the last thing I already said, which is like linked list and unlike arrays, trees don't have an upper limit on the number they're supposed to insert if you're using pointers, because yes, you can just keep inserting as long as you have space, just like a linked list. So really, this is like a linked list on steroids, as they say. Okay. Oh yeah, so applications. Here's the application thing. So multi-stage decision making. Trees can be good for decision making. Think about like a quiz. I mean, I don't know, maybe you guys haven't experienced that, but like when I was a kid, there was the magazines that had the quizzes on them. Like it was just like, yeah, it was just mostly just quizzes about like what movie should you see or that kind of thing, right? And those were like yes or no questions and you would follow a path, right? Those kind of decision stuff is not just for fun, but certain like troubleshooting manuals. Like my dad, who well, I would say works, but now he doesn't because he's furloughed. But who used to work, I suppose, in airlines, when they had a problem with a plane, they look at the manual, and the manual asks a certain questions. And based on the questions, you go a certain route, like a certain page in the manual, or a certain other page, and you look at that section, and you check what's the errors, and then it tells you what to do, right? So you're following a decision tree there. So whoever organized the manual had to draw the tree so they could figure out how to organize the book, right? So that's a big usage of trees as well. But the biggest thing is searching. Trees make data accessing and searching much, much faster and much more convenient than having to sort something ahead of time. Okay, so that's kind of all that I want to say about the introduction of trees. You can go ahead and read the rest of that. They give you an example. I suppose, yeah, they show code. I should show some code. This is a new concept to use, so I'll show some code. But one last thing, I suppose, I might have not mentioned this term, is when you have a binary tree like this, the 1 and the 4 here are considered the left child and the right child. And that's specific to binary trees because there's 2 things, so we can label them easily. If you have 3, then I think you have to go like left, middle, and right or something, so that'd be weird. But yeah, with a binary tree, we consider one of the children, typically the one to the left, to be the left child, and then the one to the right to be the right child. And then there's always only one parent, okay? So this is where it deviates a little bit from family trees. When I was talking about family trees, you have a parent and you have a dad and a mom, and they get together and they form a kid. Here, there is no such thing. You never want this, because this is technically not a cycle, by the way. This is not a cycle because you can't go back up. All it's saying is it's colliding back up 4. You don't want that. That is just going to mess all your algorithms up and not work. So you do not want to ever have 2 different nodes have the same child. Okay, never. It's a no-go. So I'll put like do not connect, I suppose, 2 parents to the same child. I want to make sure I emphasize that. When you're coding these algorithms, if you do that, the whole you're either gonna infinite recursion, or it's just gonna run forever, or it's gonna crash, or it's never gonna finish sorting. Big mess. Would the 10 be a right child? The 10 would indeed be a right child, yes. And there is no left child for that example. Okay, so you would say 8 has a right child and no left child, so it only has 1 child. So yes. Okay. Oh, and there we go. So I went ahead and wrote these properties ahead of time. They're all from the second link. So I guess I'll post the second link so you can see it. Again, it'll be on the description of the YouTube video. But yeah, what I want to do is I want to just go over these different sort of properties, and not because they're like something you just have to like memorize or something, but because they help you better understand sort of some basics of how trees work, which will make it easier when I'm trying to explain some of the algorithms, okay? So, yes. First of all, we still need to talk about what the height of a tree is, actually. So, I think, yeah, that'll kind of come up, but yes. So, let's look at the first property, okay? And now we're looking strictly at binary trees, okay? So, not ternary trees, not unary trees, but binary trees, okay? So, the first property that it says here is the maximum number of nodes at a level L, so we're calling L a level. What's a level? I'll explain in a second. Of a binary tree is 2 to the L. So first of all, what is a level? So if I'm looking at a binary tree, which again can have up to 2 children, but doesn't have to. And by the way, technically speaking, actually that one looks too obvious, this one. Technically speaking, both of these are binary trees. Like literally, this is a binary tree thanks to this level here. Otherwise, it would be unary. But just thanks to that one node, it is considered a binary tree. Now, normally you will see a lot of them that are binary, but you don't have to, right? You can see them all be binary potentially. We'll talk about that in a second, actually, that special case. So yeah, I just want to make sure I pointed that out. But yeah, okay, so what is a level? A level in a binary tree is like horizontally a sort of a layer. So like, I suppose the distance that it is from the root node has to be the same. Now what is, the distance, what does that mean? How many nodes do you have to go through to get to the root node, okay? So for example, and this is another thing, and I should point this out now. Even in Geeks for Geeks, this is a sort of an argument. So they consider 0 to be different, okay? When we're talking about height or distances from a root node, I can say that if we label these nodes, I'm going to label them like, here, I'll just make another tree. A, B, C, D, E, F, G, H, I, J, and then maybe K, okay? So I just put letters just to label them, okay? So we would consider B and C to be on the same level, okay? We would consider D, E, and F to be on the same level. J, I, G, H to be on another level. And finally, K is in its own level. And even if I draw this really bad, which you might see throughout the semester, but like, let's say I draw a tree like this. It's poorly drawn, but technically speaking, these are the same level, right? Yeah, there's 3 levels to this, here and then here, right? So be careful when you're drawing your trees not to get confused, but basically the levels are the distance from the node. Now, what I'm saying there's some sort of disagreement is, would you consider the level at the top, which is the level of the root, which is always going to have 1 node only, right? Would you consider that level to be level 0 or to be level 1? It's kind of like, do arrays start from 0 or 1? Both things will work, but depending on when you consider that, some of these properties might be off by 1 or such, okay? So just be aware of that. I'm not saying one is correct or wrong. Both are actually correct. It's just the same thing as considering whether arrays start from 0 or 1. 0 is more intuitive. Fair enough. If it might be more intuitive to you, but I think, you know, to me, 0 is more intuitive for arrays, right? Like if I start counting stuff, I start counting from 0. But we're CS people. You ask someone from maybe the math department or merely just someone that's not in CS, and they'll tell you that it just makes more sense that like the first index of a list of numbers should start at 1, not at 0. So it's a very CS thing to say it starts from 0 technically. So in fact, MATLAB starts arrays at 1, and that's what a lot of math people like to use MATLAB, right? So like, did they do that intentionally to not be intuitive? No, it's because some people make it more intuitive. So kind of the same thing here. It might be more intuitive to you, but not to other people. So yeah, just be aware that it changes some of these properties. So anyways, what this is saying is the number of nodes, again, the nodes are little circles, the maximum number of nodes at a certain level is 2 to the L power, okay? So let's plug in 2 to the L power for a couple of things. We got 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, and 2 to the fourth, okay? So what are these numbers equal to? What's 2 to the 0? What's any number to the 0 power equal to? One, right? I hope you guys are thinking one. Yeah, okay. So, my math first. What are you doing? Oh. So, in this scenario, for this to work, we need to consider that the root node is level 0. And if we do that, then this thing will work okay. Okay? Because we can say that there is a maximum of 1 node here, a maximum of 2 nodes here, a maximum of 4 nodes. However, you're like, wait a second, 4 nodes, we have 3. Yes, because technically speaking, this is a single child. But if we added the second node here, which we can call like W, then we would fill this level to the max, which would have 4 nodes. What you'll notice, you know, this might be obvious to me, but not to you because it's the first time you see this. I want you to notice that the more levels you go down, it doubles each time. So like 2 to the 5th would be 32, right? And it doesn't just double because math here, but think about it. Binary trees can have 2 children, right? So 1 makes 2, and then those 2 are gonna each make 2 each, so makes 4. That's, you get 8, 16, 32. Okay, so hopefully that makes sense as to the why it keeps doubling. Okay, so furthermore, when you look at this next level, it says that it should have 8. Is that the case? Well, we would have one here, and then this W needs to have 2 in there. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that is correct. So what it's saying is the maximum number of nodes at a certain level is easily found by saying 2 to the L. Okay. Now, if you consider level 1 to be the root node, then this is where this thing might be off. So you would have to do 2 to the L minus 1 up here. Okay. So you have to do L minus 1, and then it would work the same way if you considered level 1 to be the root level. Okay, so that would be just a tiny tweak that you have to do, but here we're going to leave it as it is. Okay, so that's the first property. Hopefully that makes you start to see how things double each time. The second property is the maximum number of nodes in a binary tree. So now, before we were talking about per layer, now we're like, the next sort of follow-up thing is, okay, cool, we know how to find out, you know, if this tree has 8 levels, we know that like 2 to the 8 is going to give us that level, right? The question is, okay, cool. Can we use this sort of same math to figure out the total number of nodes that a tree would have, okay? And in this case, we use the term height. So what is height? Height is that distance that I was talking about from the root node. And yet again, if I have a tree of this format here, you have a tree like this, okay? Would I consider this tree to be height 0 or height 1? Would I consider this tree to be height 1 or height 2? So again, this is sort of an ambiguity as to, you gotta make sure you define what you consider to be a height, okay? And so in in the Geeks for Geeks, the first thing they say right after the property is, here the height of a tree is maximum number of nodes on the root to leaf path. Path isn't the term that we're going to talk about when we get to graphs, but the path is the line per se. That's what we'll say for now. We'll revisit that when we talk about graphs. But it says here, height of a tree with a single node, so that is going to be considered 1. Okay? So we're saying that one node is height 1, and I suppose no nodes at all would be height 0. Okay? Is that intuitive? That's kind of different, because I would think that a single node would actually be considered height 0, right? You can make it work like that, but you have to change this slightly. And I think they show both examples here. So I'll show you both. But yeah, so what this is saying is, once we've established that what that means, then it means that this tree right here will be considered to be height 2 on the left side. And this tree over here would be considered height 3. So how do you define the height of a tree? You look at the node that is the furthest away from the root. Okay? So in this case, these are very nice trees. They look very, very even and whatnot. But suppose that I had a single node here that went like this. Bam! This all of a sudden became from height 3 to height 5. Okay? So we would think about how many nodes you have to sort of visit on the way there. So you have 1, 2, 3, 4, and 5. Okay? So that is how you get 5 there. Here you got 1, 2, and so on. Okay? So if we're talking about height, just count the number of bubbles, I suppose, or numbers to get to the root node. Okay? And so the formula that we can figure out using the height to figure out how many nodes you can put in the tree as long as everything is full is 2 to the h minus 1. What that means and what that is saying is that if I went ahead and here, let me go back and erase that and leave it like that. So what I'm saying is, in this case, our height is equal to 3, right? So if I plug it into the formula, 2 to the 3 minus 1, that is equal to 2 to the 3 is 8 minus 1 is 7. So that is saying that the most amount of nodes that I can have in this tree, if it's a height tree, is 7 nodes. Is that true? You can count them yourself and confirm that. We got 2, 4. We have 4 on one level, 2 on the next level, 1 on the top level there. So that is basically going to be 7, right? And so this is correct. If I had another layer, I would be adding how many nodes? Well, I would be adding 8 nodes, right? If I have a full level here. So like 2 here, 2 here, 2 here, and 2 here, right? And so that would mean that the next level would have 8 plus 7, which is 15, right? Well, 2 to the 4th is what? 16. Minus 1, 15. So there you go. It is correct indeed. Now, let's look back to Geeks for Geeks what it says, and this is what I was talking about. In some books, the height of the root is considered to be 0. So if you're that person that wants to say that one node height is equal to 0, and then two nodes like that height is equal to 1, if you want to considering that way, which might be more intuitive to you, then you have to use a different formula. In that case, you have to use 2 to the h plus 1 minus 1. And that plus 1 basically offsets that difference. Easy patch. All right? So be aware of that. I will accept both in like a test or something. This, of course, will not be on the first test, but I will accept it. But you have to clarify these kind of things. Like, what do you consider height 0 to be? What do you consider the first level to be? Because based on what these things mean, it will change how your algorithm, or what your answer is essentially, right? And what I was thinking with algorithm was that when you're implementing this, when you're implementing some of these homework assignments that I'm going to give you, make sure you stick to one system and then follow that. Otherwise, your formulas will not work out. So yes, okay. We got, I think, 3 more to go. So that hurts. I'm going to the dentist tomorrow. So, all right. In a binary tree with n nodes, the minimum possible height or minimum number of levels is log n plus 1, base 2 as usual. So we talked about the max amount of nodes that you could have in a tree of a certain height. Now we're trying to understand what the minimum possible height would be of a tree if it had this many number of nodes. So if I told you, hey, I got 10 numbers, okay? I got 10 numbers that I'm trying to put in the tree. It's a binary tree. How squished can I make the tree to keep the height the lowest possible? Okay? Well, it's an easy way to do it. It's just a little to try to draw it out. The first level can only have 1 node. The second one, 2 nodes. The third one, 4 nodes. So we're at 7 so far. So we need 3 more nodes. So there's no way that we can do this without adding 1 more level. If we do add 1 more level, then that's fine. We have actually lots of places where we could put them. We could put them there. We could also, I don't know, make this artistic and put it like that. I don't know, whatever, right? But there's no way that you could do this tree without having that extra level at the bottom, right? And so this, of course, was the experimental way, but mathematically, you can do that by just running it with the logs. So you can say 10 plus 1 and take the log of that. However, when you're doing that, this is the Geeks. Geeks doesn't actually say this, but you need to do the ceiling function on this. Yeah, you need to do the ceiling function, I think. Yeah, you need to do the ceiling function. Otherwise, it will not work. Okay? Because when you do this, log 2 of 11 is equal to something like 3.3. Let's try it. Let's just kind of run it. Log 2, 11. 3.45. Okay, so close enough. The point is that you can't have half a level. Well, I mean, you do have a half a level technically here, but like I'm saying is that's not a number that we want to consider, because technically the height of this thing is we got 1, 2, 3, 4 nodes, right? So H4, depending on again what. See, again, this is where you got to figure out what are you considering height 0, because like if you give an answer 4 or you give an answer of 3, then or 5, you know, like this could all be valid depending on what you are considering to be height 0. So we want to go back and clarify if I ask you in a test how to answer that, or in general to anybody when you're coding this. So we take the ceiling function. Ceiling function just means round up. Floor function, which is the opposite, means round down. Always round up so you can make sure you have a right value. So in this case, it would be 4. Okay, so that means there's going to be at least 4 levels here in this tree. It's impossible to do this. Here's another example you can try at home. 50. Okay, either draw it by hand to prove it, and then do the logarithm function, and then you will find out that this is going to be about, well, let's see, will be 8, 16, will be 4, 32, 5, so 6. You're going to need, I think, 6 levels. You're going to need the 6th level. The 6th level is not going to be full, but you'll need 6, I think. Assuming that we're considering this to be 1 level here. If we're considering it to be level 0, then I suppose that this is going to be on level 3, 2, 1, 0, which in this case that would be 7, but whatever. Okay. And that's pretty much where I stopped, so I'm going to have to write down the next 2 properties. A binary tree with L leaves has at least log L plus 1 levels. You know what I think it is? Because I do remember Geeks for Geeks having the ceiling and floor function. I think something happened with their code because I see question marks. Those probably means that those characters are not being printed out correctly. That's probably why. And they do point out, by the way, for the previous one, that if your thing is off by 1 because you consider height to be different, you can just plus or minus 1 it out, like here, okay? But anyways. So a binary tree with L leaves has at least log L plus 1 levels, okay? So this is looking at the number of leaf nodes, okay? So like if I'm looking at the tree like this, how many leaf nodes does this tree have? Okay? yes, you're gonna, well, I wasn't gonna put it because I wanted to make sure before I did the ceiling or floor on that property, but yes, you are gonna have to put one, which is why I was pointing out the question mark stuff. But yes, I'm assuming yes, you probably have to seal it because there's the word at least. So yeah, but we'll show that in a second here. So yeah, how many leaf nodes do we have here technically? Let me draw that one nicer. In this case, we have, this is a leaf node, this is a leaf node, leaf node, leaf node. How many single parents do we have here? This is single parent, and that's it. How many parents have 2 we have here? Those. So I guess I'll put a key in here. And then that one. So this is two children, one child, and then 0 child, which are the leaf nodes, right? So we have 4 leaf nodes, okay? What this is saying is, if we have 4 leaves, you know, how many levels do we need to have in the minimum case, okay? This, of course, is not really the minimum case, because could I draw a tree that was shorter, less height, but still have 4 leaf nodes in it? The answer is yes, I can. Just like that. Well, that's pretty much the one I've been drawing for quite a while. That has 4 leaf nodes. It has 3 nodes that have 2 children. Okay? So technically speaking, I have that's kind of trippish here, that I have different number of nodes. But yes, here you see I have 4 leaf nodes on each example. I have 3 nodes that have 2 children, but the example on the top has 1 extra node that is a single child. So that's kind of cool. I guess this is pretty good. So anyways, mathematically we're saying what is the least height, which of course would be this example here. And mathematically we can figure that out by just putting in the number of levels plus 1. So how many levels do we have? Again, what are you considering to be level 0? If we scroll back up here, we're saying 2 to the 0 is level 1. So level 0, level 1, and level 2. We'll say that. And if we do that, then it is log 2 plus 1. And oh, wait, sorry. With L leaves. So here L is the number of leaves. So that's a 4. My bad. Apologies for that. So in that case, it would be 2 plus 1, which is 3. And as we can see, there are indeed 3 levels here. Levels 0, 1, and 2. So 3 levels. Okay? So yeah, that's that property. So again, that doesn't mean that you can make it taller, because I mean over here on the left you can see that this is 2 levels higher actually. So there's 5 levels on the left one, and still only 4 leaves. The property is saying the least amount of levels, not the most amount of levels. Okay. So last property, we got 2 minutes left of class. So next time, and next time will be, of course, be on Monday, because we will not have class on Wednesday because you have your exam. I will go ahead and talk about the special kinds of trees, which we didn't get to today, and then we'll start on traversals probably. And like I said, I will release the assignments. I guess in that case, I'll probably release the assignments on Monday. Because if I release them early, you guys are going to have a bunch of questions. So I'd rather talk about traversals before releasing them. But for now, let us talk about this final property. It's more than nodes. I hope I'm writing this correctly. It is kind of difficult to talk about something and be writing something completely different and not get the two things confused. So we'll see if I got it right. So in binary, I guess in a binary tree where every node has 0 or 2 children, so that means we can have either this or this or this, but we can't have that. That is no go. It's also no go because again we still have this issue here. So we're saying in a special tree that has 0 or 2 children, the number of leaf nodes is always 1 more than the number of nodes with 2 children. Okay, so this was kind of hard to prove, I suppose. So they don't even prove it. They actually just say to go look at the handshaking lemma and tree. Go look at that link and talk about that for the proof. But essentially, it makes sense from a conceptual view, just hard to actually mathematically prove. But what they're saying is, when you got this special kind of tree, and this is a special kind of tree where it only has 0 or 2 children, we are saying that we can very easily tell you how many leaf nodes there are if you know how many nodes with 2 children there are, or vice versa. Okay? So in this case, we have 4 leaf nodes, and we have 3 sort of internal nodes that have 2 children. In this one here, on the right here, we have 2 leaf nodes and only 1 internal node with which two children node. Okay, so as you can see, it's always 1 less. Like, let me do maybe 1 bigger example, and then we'll call it a day on that. I guess tip for when you're doing these trees, start wide, like start like that and then go smaller, because otherwise you do what happened with me, you run out of space. But yeah, so in this case we can see, let's count the internal nodes first in this one. 1 2 3 4 5 6 7. So the thing says that we should have 8 on the last level, which hopefully you already see that is true. 1 2 3 4 5 6 7 8. Okay, so that's the last property. So hopefully this starts to kind of get your brain going on trees and a little bit about how they function, the concept of height, levels, leaf nodes, internal nodes or parent nodes. And next time, like I said, we will talk about the types of binary trees, which is just sort of a conceptual thing, and then we will start talking about traversals, which is how to actually tell somebody else what your tree is. Like, drawing pictures is great, but good luck trying to draw a picture on a computer and make the computer understand what you're trying to say. So traversal will help you how to actually translate the hierarchy of a tree into text that you can then feed into a computer. So that's a pretty cool concept too. Okay, but that's it. Was it log L plus 1 or log L plus 1? Oh, this should be like that. Oh, good point. I believe it should only be like this. Like, it should be, you should do the log part first. Like that. Don't do the L plus 1, I think, inside. Did I do it inside? No, I didn't. Yeah. So yeah, this one is inside for the third property, but for the fourth one, I don't think it should be inside. Yeah, no, it should not be inside. Nobody says so. Good point. Thank you for pointing that out, so otherwise people get confused. All right. So this officially concludes the lecture. So since we don't have a review day, I thought I'd hang around for a few minutes and answer questions about the test to help you out for the exam. So yeah, I already see the first question. So let me go ahead and put in here a title to this. So the test is going to be on Wednesday at, because we have the 2 times, we have the 1 and the 4 p.m. times. What I've done is I went ahead and made the test available starting from 1 p.m. all the way until 6 p.m., which means that you can take it at any time in between. So if you like to start at 4 or you like to start at 1, you can do it for both. In fact, in theory, you could start after 4. You could even start at 5:59, but then you're only gonna have 1 minute to do the test, because what happens is the shutoff is at 6 p.m. At 6 p.m., you will not be able to submit your test after that. So make sure you don't wait until last second. Submit it like at 5:59 at least, okay? But yes, you have that opportunity. The duration of the test should be 1 hour and 15 minutes, but I give you 2 hours. The extra 45 minutes is for logistics of the test, which means like uploading files and whatnot. That's what I was doing earlier. I was doing something and I forgot because I had to do other stuff, and now I remember. What I was going to do, and I will still do, unless I totally forget again, is I have a little tech thing on Canvas that is sort of like, it's not a practice test, like, you know, for practicing the concepts, but it's for practicing the system on Canvas, which is like submitting text on Canvas and uploading files on Canvas, like during an exam. So I'll make available that, like, give me like an hour maximum after we finish the video here, and I'll make that public, and so you can practice the, like, time yourself how long it takes you to draw a picture or whatever and upload it, because some of these questions require you to upload files onto Canvas, and if you have never done it before, it might be a good idea to set up that sort of streamlined process, whether it's through an app that takes a picture of a drawing, or if you're doing it on Paint or whatever, the process of converting that into a file that you can upload. Whatever it is that you need to do, better do it now, because I don't want people coming in during the test like, I don't know how to upload my file onto Canvas. No go. I'll be really mad because I'll check if you did the practice, and then if you didn't, then I'll be like, no sympathy. So I'd rather you do that now and get that sort of figured out. You know, and I recommend you try it. If you intend, because what you can do for the test is you can download the test, like, not download, but like you can copy and paste like a question, do it on your computer, and then upload it. And if that's the system you're going to do, it's good to practice that to see you don't run into like, oh, I can't pair my phone to my computer or something to scan it or whatever. So, you know, it's better to figure that out now. So anyways, just making sure. If level of root is equal to 1 for the first property. Oh, shoot, I thought that was a question on the test. Sorry, I'll get to you. So if level of the root is 1 for the first property, then the maximum number of nodes at level L of a binary tree is 2 to the L minus 1. Yes, you're correct. Oh, yes, you were right. I have a question. The Mergesort recurrence relations. Will we have to submit one PDF with all our answers? So in the test, you have no problem. There are questions that require you to write stuff. They're like essay questions, but they're not really. They're like what would be an example of something that is not on the test? Let's say that I was asking you about virtual functions, and I said, when is a virtual destructor useful in C++? And you would write something like, a virtual destructor is useful when you are doing casting, you know, up and down casting, and you create an object of the parent class, or you create an object of the derived class, and then you cast it to a pointer of the parent class, and then call delete on that pointer, and it's only going to call the destructor of the parent class, not the derived class, which could cause memory leaks, right? So that's something that you would actually write out and explain. Those are the kind of questions that you'll see mostly on a test for pretty much almost everything. There is other kind of questions, like, for example, there's going to be sorting question, right? You're going to have to write, I'm going to give you a list of numbers, and you're going to be like, explain how Quicksort works, and then show me with these numbers how you'd actually do it. For that kind of question, because you probably want to have the ability to draw and stuff, especially for like Mergesort with all the divisions and whatnot, I made it a file upload question. So you can individually upload a PDF or a JPEG if you have a scan, although I think PDF would be nicer. But JPEG's okay, or PNG. No other formats, or like GIF, no, or TIFF or whatever. Don't do that. And then you could type your full answer there, and that gives you more flexibility. However, at the end of the test, I also have one upload. So if you prefer, you can do the full test by hand, and then upload the entire test at the end like that as one file. I will also accept that, because on the spring, I did it the first way, and some people didn't like the whole having to do different uploads for different questions. And so we tried a full upload, and then some people didn't like having to do everything in one big upload because that put a lot of pressure at the end of the test trying to scan and whatnot. And so the middle ground was you have both ways to do it. So it's your choice. So if you prefer that, good. The thing is, You're getting 45 minutes to do this, so there should be no reason why you run out of time. And like, oh, I was uploading my test at like 5:59 and the scanner wasn't uploading fast enough or something. Don't put yourself in that situation, essentially. Okay? So yes, if you have a tablet or something, probably your best bet, but of course we don't all have the means to get tablets and fancy pencils and whatnot. So yes. My understanding is that the relation T of n divided by plus Cn, where the first part is the recursive call on the two sublists and Cn is how long it takes to merge the two sublists. I just want to make sure that it's fine to use Cn since the exact number compares with variance. Yes, that is correct. That is fine to use. Will our worksheet grades or any other assignment grades be finished by the exam day so we can review our work? Good question. I don't know where the TAs stand on that, but I'll remind them. I usually try to do this whole 2-week turnaround time, so I don't know. I do believe that they posted like up to at least assignment 3, because I get emails like that they publish grades. I do know that once in one scenario they forgot to actually publish, but they had finished grading, so I'll remind them on that. If you would like to review before the grades are published to make sure that you understand what's happening or what you got wrong and whatnot, just go to the office hours of the TAs and talk to them, and I'm sure they can go over that as well. Unfortunately, I'm pretty sure they won't be able to get the second worksheets graded before, but you can definitely talk to them to go over the answers of it. In the case where the question is a file upload, can we type the written explanation and draw the actual sorting? Yeah, sure. If it, whatever is the fastest way for you to get the information that you need on that paper or in that submission, all power to you. Will we have to look at a piece of code and find the recurrence relation from that code fragment? Yes, you will most likely have to do something of that sort. Pun intended, I guess. I don't have assignments 2, 3, and the worksheets 1 and 2 graded. I shall talk to the TAs. I'll send them a DM on Discord and see. Well, I don't even know when assignment 4. You mean assignment? We skipped 4, so I'm assuming you mean assignment 5, right? Or 2, 3. I don't know. I have no idea. But the thing is, since we delayed the submission so much, like I don't know when they were due, which I don't know when the 2 weeks will be, but I'll let them know for sure. I have a message from the TA right now. Wow, it's a big message. So yeah, I'll let you know with them and see what's up. All right? Yeah. So definitely, I would say that they should definitely get going on that. So I'll tell them to make sure that they at least get 2 done, and maybe the worksheet. Maybe they should emphasize on getting the worksheet done, because then you can actually see the answers to that. But thank you for letting me know. You really guys should have told me earlier, because like right now I can tell them, but like if I told them before the weekend, they would have had like the weekend to do it. Now they have like middle of the week, so hopefully they can achieve something there. But I'm so sure I saw more stuff graded. Maybe I was 202, I don't know. How specific should the drawings be for showing how a sorting algorithm works, like from worksheet 2? Well, you can pretty much expect the same questions that you see in the worksheet, especially for the sort. There's only so much that I can do. But so with something like Quicksort, every time you do a swap, I would encourage you to rewrite all the numbers, because the TAs who are grading this, like the worksheets, they want to make sure that you understand what's being swapped and whatnot. That's why I think like Paint might be a good solution, because then you can just copy and paste it and then just swap the 2 numbers. So I would recommend you do that for Quicksort. For Mergesort, you can do all the lines, like you can do like let's say we're sorting these numbers. You can go ahead and do something like this. And then when you're merging together, that's the part where you gotta make sure you either explain like how the merging works, like you look at a left index, you look at a right, like 2 indices for the left and the right sublist, and then you merge them based on which one's smaller and you shift by 1. And as long as you explain that on the side here, then you can just go ahead and say that this becomes that, and this becomes that, and then you can say that this becomes that. Like, that's okay. That's not a lot of drawing, but this explanation has to be right, and has to be like thorough for the case of like where you have to append. And if you end your explanation, you can use a special case like if you're merging the following list together and you just come up with some list with and then say you're merging it with like this list, then you would append this entire list here. Like you can do that, and then that way you can just do that here. Okay, so basically you want to establish confidence in the TA that you know how the sorting algorithm works. And if you do that, then I'm sure he'll be like okay with it. And of course, get the sample numbers given. The number of items in the list you're sorting, by the way, I believe is 7 each. So it's small enough that you don't have to write like a billion different lines with numbers, but still detailed enough that you'll get, especially with Quicksort, you get good partitions. Like I try to intentionally pick one with a median as a pivot so that you could have like decent looking partitions and not like you know everything goes to one side or the other. So it's both drawing and explanation for this sort. Yes. So yes. Oh yeah. See, shoot. You know, they told me that last time because last time I came up with these worksheets last semester, and I just picked numbers, and I never realized that there was too many numbers and they would take forever. So I made a mental note to lower the number of numbers in there, but I forgot to do it. So I apologize for that. But hey, it's good practice through repetition that you have to do that. So sorry, but hey, at least you probably burn it into your mind how to do the partitioning now. Do we have to explain every step we do on the drawing? So kind of like how I said here, you explain the key steps as a general explanation, but you don't need to explain for each individual one. Like, okay, I'm comparing 1 and 5. Now I'm comparing 2 and 5. Now I am appending 5 and 8. You don't need to do that much. You can just explain how that works and then just show me, okay? For Quicksort is the one that it might be a better idea to actually show how the swaps work because it's very easy to get that confused. But some people sent me like examples of how to explain stuff like, oh, one person did an Excel one. They were doing Quicksort in Excel. That was a good idea too. That worked out really well. So talk to Tacticool on Discord. He had a really good system set up, which is what I recommend you guys do for this stuff. So yeah, because with Excel, he just kind of like extend the columns down, and as he would change things, it would extend them. I was like, wow. And the whole point of this is not just that you know the algorithms, but like you have a system set up where you can do things quickly so that you can spend more time on the questions that actually involve more effort, like the recurrence relations primarily. So I'm going to open up the test here to see if there's anything in particular that I would like to call out on. So I finished the test this morning. And I told the TAs to take a look at the test and get back to me on if there's anything. So I might still change the test between now and Wednesday, but they're going to give me a review of the test, which is why one of the TAs was messaging me. So that's good because then I'll segue and say, by the way, get these things graded. So if I look at the test, by the way, right now it has I believe it's about 18 questions, I think. Because I think it says 20, but 2 of them are not questions. They're like introductory things. But they count as questions. I think I have to do a preview to better see this. So it says 19, but 2 of them are instructions. So 17 questions so far. And then the file upload ones that I have are the recurrence relations I have as uploads. The sorts I have as uploads. And nothing else is upload, but I do have that upload at the end. So if you choose to do any of the other ones as more than just text, you can. Just number them all or label them and then put that on the upload at the end, okay? So definitely review the older stuff, like big O notation, asymptotic complexity, the logarithm rules. At least have them in a piece of paper somewhere near you so you can use them when you're doing the recurrence relations. But also the asymptotic complexities. Like, remember, I guess I should clarify this, growth rate. So the question is going to ask you the same way as the worksheet. You know, order each of the following by asymptotic complexity by growth rate. Okay? And when I say growth, I'm saying how quickly it becomes slow. Which means that if you have something like n and n squared, and maybe you have maybe a log n. Okay, so if you're starting these by growth rate, you start out with the log n, which is the fastest. It's the slowest. See, this is where you gotta be careful how you say this. Log n is the slowest to grow, which means that it doesn't get as slow quickly. It's the fastest algorithm, but it's the slowest growth rate, which is good for us. We don't want it to become slow. So the ordering of this would be like that, okay? So just make sure you don't screw this up and put it backwards, all right? But yes, some of these questions are right from the worksheet, just different numbers, essentially. That's why I said the worksheets are your study guide. And I do have some trick. I'm not gonna lie. I had fun making the different asymptotic complexities for the test. Some of them require some logarithm math, so don't just dismiss them. Okay? Yeah, that's all I'll say about that. I had fun with that question. I have some questions about concepts where I say like explain this or explain that. If you're giving this scenario with this scenario, you know, what happens here or there in terms of big O, theta, omega, different complexities. Remember, if I say something like n squared, technically anything less than n squared can fit in n squared. In fact, any algorithm is O of n exponential or n factorial because that's the slowest, right? So everything would be technically in that category, the subcategory. You do have pieces of code, just like the worksheet, where you got to figure out the asymptotic complexities, recurrence relations, all that stuff. To be fair, I split some of those codes into different questions, so that's why you have 17 questions, because like in the worksheet you have like I think 4 pieces of code or something, or 2 pieces of code. Here I made them separate questions just to make things simpler. Then you have like the worksheet as well, like the 2 questions about like, I think the worksheet was like inserting into a linked list, the big O of that. You have 4 of those in the test. Make sure you explain your assumptions. There's a stack and queue question, so make sure you refresh that. Then it goes into sorting questions, like conceptual sorting questions. Remember what stable sort is, in order sorting. We talked so much about stuff today, so that's good. Make sure you review all the sorts: bubble, selection, insertion, quick, and merge. Those are the ones we talked about. And just like the worksheet, you will have a merge sort and you have a quick sort question like that. And then you have multiple recurrence relation questions. One of them being very similar to the one I just posted on Discord. So just ask somebody if you're not on Discord, or ask me and I'll send it to you by email if you're not on Discord. But I posted a question from my old test in the spring. I took that question as a template and I made a new one very similar to it. It is the highest point question on the test. So imagine that I use the same question. Would you have been able to answer that correctly? If not, then you know what you need to study. And just like last semester, the question is the highest point question in the test, but also if you get it completely correct, you get an additional extra credit. So it is in your interest to make sure you know. And then it's of course the topic of that being recurrence relations. Because I mean, heck, we spent like 3 weeks on that stuff. So gotta milk it out in the test, you know. So yeah. For given the asymptotic complexity, do we need to type the symbols O, theta, and omega in the test? So yes, I think that would be ideal. But if not, you can just write the word omega. So like, I'm okay. You know, I understand, like, you know, we're CS people, but we still can't do basic stuff. It's okay. No, it's frankly the truth, you know. Like, too much effort trying to figure out what the ASCII value for omega is. So if you just write omega like n squared like that, that's perfectly fine with me. However, I did, as part of the question, use the symbol for omega. So if you're smart, you know, you can copy and paste that symbol into your output, into your answer, and not have to worry about Googling how to put the omega symbol. But frankly, just go with that. Who knows? If you put the bottom one and like there's a glitch in the system and like disappears, that'd be bad. So, but yeah, it's a good point. So if you have any issues with like the symbols, like the Greek symbols, just write them out by the name. Also, while we're in that token, if you need to write something in exponential, you know, you can use the superscript, but you can also just do the little hat symbol. Or if you really, I mean, I think that's the best thing with the hat symbol, but to represent this. But I suppose you could say nx2 like that, and I also understand. Or basically write n to the power of 2. just if we understand what you're saying, that's good. So just put yourself in our shoes. Is what you're writing clear? Do we understand? And if so, we're good. You know, we understand that you're not gonna do magic here. You're limited in time. Frankly, I'd rather you focus on the content than trying to Google how to do this symbol on the test, right? And yes, there is a tool in the boxes that has. I actually use that in writing the questions because I actually want to take the effort to like do the exponent symbols and stuff. So there is indeed a tool that you can use. It's a little superscript. In fact, I might be able to show you that. Yeah, this way. All right. I hid all the questions so you can see just that. This is actually I'm running the test right now in preview mode, meaning that like it's like what you guys would see if you took the test right now. So you can see here you got bold, italic, underline. You got the little exponent symbol, subscript if you really want to use that, bullet points. You can attach. I would not insert media into the text things. I've seen people do that. It works, but be careful if you're inserting it that you're uploading it and not linking it externally, because like if that link dies, then you're screwed. So yeah, be careful about that. Embedding images. There's math equations and sizes, and if you go to the right here, you can actually change this to pre-format it. So if you want to write code snippets, you can do it that way. So yes. All right, so there you go. You get to see the look. I'm showing you the test. And now it's gone. All right, so it includes the omega. I don't know if it does. I had to actually copy. I actually have to copy and paste it. So yeah. But hey, if you're hardcore, there's a button you can click and switch it into HTML mode, and then you just write out flat out HTML, and it'll look beautiful. It'll be a masterpiece. That's actually how I do some of the Canvas pages. Just pure HTML. It's just easier, but it does involve knowing HTML. So yeah, focus on studying, not on learning HTML. Probably a better way. All right, I'll take like 2 more questions. Will the questions on the test explicitly state what method we should use for solving the recurrence relation? I think I put a recommended method. Like I said, you can use the master theorem for this one. However, understand this. When you're solving it by the old method, the complicated methods that I showed you, you get big O. When you use the master theorem, you get big theta. You don't technically get big O. So if the question asks for big O, you can't use the master theorem. But if the question asks just to solve it, then and it doesn't specifically say big O or theta, then you can just assume it's theta. So essentially, I did try to explicitly state it in the question that you can use either one. Okay? More questions now. Speak now or hold forever your peace. If you have time, could you run through an example of simplifying recurrence relations involving logarithms? Doesn't solving the recurrence relation give big O and theta? Solving a recurrence relation gives you both, but master theorem only gives you theta. I can't run through big example on recurrence relations, but what I can do is remember, I think it would be better if you, because I don't know if you're asking about the logarithm properties or because what do you mean by simplifying? Typically, if you see if you see a recurrence relation with an n divided by something, that involves logarithms. That is going to be your sign that it involves logarithms, and your general solution will be something of the format of like, that has to be equal to I, and then you can use logarithms and that kind of stuff. I think that's kind of what I can recommend for that. You're better off watching the video again for that. Or maybe watching my spring video on that as well. Otherwise, send me a DM in Discord and we can go over like an example at another time. Before the test, of course. All right, one more question. Going once. Going twice. If you have additional stuff, you can You can post on Discord or send me a message, and you know, within reason, I'll try to get back to you. So I am going to the dentist tomorrow, so I might be AWOL for like half the day. Who knows? I have no clue. Will there be multiple choice questions? No. Everything is short answer or upload a file. Yeah. Yeah, there's nothing I really can't think of anything. So I mean, it's okay. It's most of the questions wouldn't be able to be answered in like 2 words, so that's why it's short answer. Yep. All right. I wish you all good luck. Remember, there's no class on Wednesday, so other than the test, you are free until next Monday, when we shall continue talking about trees. Let me know if there's anything else. Until then, best wishes for the test. You will be getting an announcement on Canvas with an access code for the test exactly at 1 p.m. So check your email or just check on Canvas announcements for that. You should have gotten the Canvas announcement exactly at 4, mentioning that the test is happening on Wednesday. So just the same way you got that, you get the access code. If you haven't gotten it by 1:05 or something, then start asking. But you should get it. I already set it up to automatically send it. So good luck, and yeah, do good on the test. Make me proud. See you guys.